And we're back in the Simpkins Physics Corner, Physics Academic, little friction action. So I got you a video answer key here, so let's jump right into it. A 65 Newton boy sits on a sled weighing, force of gravity. The coefficient between the sled and the snow is 0.012. What is the magnitude of the frictional force? The sled is pulled at a constant speed by a rope held horizontally. And what is the tension of the pull in the rope? Okay, so let's drop it down here. We have a 65 Newton boy sits on a sled weighing 52 newtons. So if we have the boy is 65 newtons and the sled is 52 newtons, how much total force of gravity do we have acting down on our system? We have 65 plus 52. So instead of thinking about them separately, I'm just going to put them all big together in one big blob of mass and call it 117 newtons. Now that is the newtons, so that's the weight, force of gravity. 117 newtons is down. If you're on a flat surface, what can we say about the normal force up? Oh, it's the same as the gravitational force down. And it also notes that we are going at a constant speed, pulled by a horizontal rope, so that's our applied force. And it says that there is friction going on here, and of course there has to be because we're moving at a constant speed. So the force of friction to the left, the applied force to the right has to be balanced. So first question says, what's the magnitude of the frictional force? Let's go ahead and look at our equation sheet, and we see FF equals mu Fn. Well, we have those two things, so let's plug them in. We got 0.012 times a normal force of 117 newtons, and let's see what that will yield for us here. We have 0.012 times 117, and that's going to get us 1.4 newtons. That is a piddly amount of newtons, all right, but that is what we have here, so 1.4 newtons. The next question says, what's the tension in the rope? Well, guess what? If we are moving at a constant speed, then the force to the left must be balanced with the force to the right. So there's the answer to part 2. What is the tension, the pull in the string? You can call that FT if you want. I call it the applied force, but if you're pulling a string, sure, let's call it tension. Nice, not too bad for that one. How much force must be applied to push a 1.3 kilogram, book, that's mass is measured in kilograms, so that's 1.35 kilograms, at a constant speed if the coefficient of sliding friction is 0.3, just 0.3 there. So let's go ahead and draw this one out. We're going to push the book across the desk at a constant speed. Constant speed means the forces must be balanced. And since we're on a flat desk or a flat surface, we know that these two forces have to be balanced as well. So let's jump into it. Now, you would be mistaken if you would write 9.8 as Fg. You would also be mistaken if you were to write 1.35 as Fg, because we know that Fg is neither of those things. It is Fg equals mg from your equation sheet. So the mass here, 1.35 kilograms, times the acceleration due to gravity, 9.8 meters per second squared. If you multiply those two things together, then you will get the force in newtons, the force of gravity acting on this box. Again, because we're on a flat surface, the normal force must, that's a 3, must be equal to that one. So there's that guy. And it says how much force must be applied to push it at a constant speed. Well, where do we go from here? Well, our FA has to be equal to our FF if we want to move at a constant speed. The forces have to be balanced. And FF just so happens to be equal to mu Fn. So let's plug those guys in. We got mu is 0.3. Fn from our diagram is 13.23. And our applied force then, since it's balanced with the force of friction, we use the force of friction equation. Sorry, this thing's skipping all over on me. Is 0.3 times 13.23, which is going to be pretty much, I'm rounding it here to 4 newtons. So that's how much force would be applied to move it at a constant speed if the coefficient of friction is 0.3. Rocketing and rolling. Next one, a horizontal force of 400 newtons, so let's draw this guy, 400 newtons, is required to pull a 1760 newton. All right, that's telling us about the, force of gravity. Careful. Always look. If it has kilograms, that's mass. If it has newtons, that's force. All right, across the floor at a constant speed, find the coefficient of sliding friction. Ooh, we got to find the mu for this one, the coefficient. Remember, this means the mu. It means that little decimal number. Well, this is the applied force, and we're moving at a constant speed, so the force of friction has to be equal to that. It has to be also 400 newtons the other way. Then the force up, the normal force, has to be equal to 1760 newtons, just like that. And if we look at mu, and we look at our equation sheet, the only place that shows up anywhere is FF equals mu Fn. So let's go ahead and plug our numbers in. FF, 400 newtons, equals mu times our normal force, 1760 newtons. 1760, 1760, and we're going to go ahead and solve for our mu here. So 400 divided by 1760 equals 0.23. So that's your coefficient of friction for moving at a constant speed. Now, today I introduced this idea of accelerating with friction. And this is a little bit of a new idea, so hang on tight for this one. If a 1500 Newton force, so that's our applied force here, a 1500 Newton force is applied on a 200 kilogram crate. Remember I told you guys you could write the kilograms inside the box to make sure you don't confuse it with the forces. Is used to move across the floor. If the coefficient of friction, so since we're accelerating, I'm going to draw the force of friction arrow a little bit shorter, right? Because if we're accelerating, it means the forces are unbalanced, and so FF is no longer equal to FA. And this is where things get a little tricky, but let's see if we can't handle it. So over here, we got the mass is 200, and the mu is 0.25. So if the mass is 200, we can get the weight, force of gravity, by doing m times g. So this would be 200 kilograms times 9.8 meters per second squared, which is looking something like this, 200 times 9.8. All right, 1960 newtons. Now, if that's the force of gravity down, then the normal force up, because we're on a flat surface, has to be balanced. It has to be 1960 newtons as well. The thing that's not balanced, though, are the horizontal forces. So let's dig into this a little bit. The reason things accelerate is because they experience unbalanced forces. So look in this direction right here. In that direction, we do not have balanced forces. We have unbalanced forces. And so to handle that, we say sigma F equals ma. We say the sum of all the forces acting is going to cause the mass to accelerate. What are those forces? Well, there's the applied force to the right, and there's the force of friction opposing it to the left. All right, and so that is how we expand our sigma F expression. And so to fill this in, we have 1500 newtons minus, I'm going to go ahead and put the equation here, mu Fn equals ma. Now check it out. We know mu, we know Fn, so we're going to plug those guys in there. So we have 1500 newtons minus, we're multiplying together, 0.25 times 1960. And that's going to be equal to 200 times A. So we're going to divide both sides by 200 to solve for A. Now there's some intermediate algebra. There's some steps in between, right? We have 1500 minus, make sure you multiply 0.25 times 1960 together. That gives you 1010. Divide that by 200, and we're looking at something like A equals 5.05 meters per second squared. So don't miss the big idea for this one. Anytime you see this word accelerating, you're going to have to jump to use sigma F. In the last three examples, if you see the word constant speed or at rest, you can set the forces equal to each other. But if you're accelerating, you can't do that. All right, let's try this one. An object weighs 40 newtons. Wait. Force of gravity. There it is. All right, so there it is right there. And the coefficient of friction, I'm going to write that on my list of knowns over here, is 0.35. What is the frictional force between the object and the surface? Well, if Fg down is 40, then Fn up must also be 40, because we're on a flat surface. Up and down forces are balanced. And the first question asks us, what is the frictional force? And so let's go ahead and find that. So the frictional force is mu times Fn from our equation sheet, which in this case is 0.35 times 40, which we can calculate to be 0.35 times 40 is 14 newtons. So the force of friction is 14 newtons. A 20 Newton force is applied. Oh, wait, 20 and 14. Are those balanced or unbalanced? Oh, those are unbalanced. So we're going to have acceleration. If you have, anytime you have unbalanced forces, you're going to have sigma F equals ma. So it says, what's the magnitude of the unbalanced force? Well, we have 20 minus 14. So 20 minus 14 is 6. And the mass of our box, they would do that to us, wouldn't they? And you see what we got to do, right? You would be mistaken if you plug in 40 for the mass, because it's not the mass. It's the wait, force of gravity. But because we know Fg equals m times g, we can solve for mass pretty quickly here by just doing this. And we would divide both sides by 9.8. And we get our mass here. So our mass can be whatever 40 over 9.8 is, which is, on our calculator, 4.08 kilograms. Nice. So that is a little detour we had to take, but now we can go up here, 4.08 kilograms times our A. Let's see, what was our A? Oh, I don't know yet. Got to find it. Divide by 4.08, divide by 4.08, and A is going to be 6 over 4.08. It's going to be 1.47 meters per second squared. Nice. Sorry, my PowerPoint really likes to skip ahead on me. Good. We got one more on our practice sheet. Let's see if we can handle this one. Mr. Johnson drags a cart across the hallway and exerts a force of 200 newtons. Wow. Strong guy. The cart has a mass of 50 kilograms and is being accelerated. Okay, so we got a couple unknowns here, don't we? We have to write our list over here. We have 50 kilograms, and we have an acceleration of 2 meters per second squared. It says, what's the force of friction? Whew! How am I supposed to figure that out? All right, well, let's see if we can get some more forces first. Can we get force of gravity? Oh, of course. Wait. Force of gravity, always calculated by doing M, 50 kilograms times 9.8. Which is going to yield, times 9.8 here, it's going to yield 490 newtons. And if there's 490 newtons down, there's got to be 490 newtons up. Not so bad. Now here's where it gets tricky. We are accelerating, so the forces are not balanced. And so what happens here is we have sigma F equals ma. Anytime you see the word acceleration, you're thinking sigma F equals ma. Why? Because there's an A in there, okay? And if we look at that, the sum of the forces comes from my applied force minus the force of friction equals ma. So we don't know what the force of friction is yet, but we do know there is some, and we can find out what the number is by using sigma F equals ma. So let's do it. 200 newtons minus FF equals... All right, let's see. M is 50 kilograms times A is 2 meters per second squared. So that's going to be 200 newtons minus FF equals 100. Now, how do we solve this? Well, we could subtract 100 from both sides. That would be 100 equals, and we'd add FF to the other side. And so it looks like FF is a nice even 100 newtons. So FF is 100 newtons that away. Yes, of course I want to keep it. I just did all that hard work. Let's go back here real quick. Oh, sorry. And that is number 6. So make sure you're checking these out. Make sure you understand the difference between when it says constant speed, like in our first 3 examples. That's nice and easy because you can set the applied force equal to the friction force. But if you see the word acceleration, you want to immediately think acceleration, A, F equals ma, and you're going to have to figure out the overall or the net force for that. All right, so happy physicsing. Until next time, I'm Mr. Simpkins in the Simpkins Physics Corner.